Sines, and now we want to work with law of cosines. So law of cosines is going to be used to solve oblique triangles again, non-right triangles. But this time it's when we have three sides given or two sides in the included angle. Now remember, side, 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 and side angle, side were both ways that we could prove triangles congruent. So we don't have to worry about an ambiguous case here. If we get a triangle, it's the only triangle, the one and only, and we don't have to worry about anything else with that. Does that make sense to everyone? All right, so law of sines said the sine of angle A over side A is equal to the sine of angle B over side B equals sine of angle C over side C. But law of cosines deals with the cosine, not the sine. And there are three of them that we can look at, notice patterns, and figure it out. Okay, so the first one says a squared equals b squared plus c squared minus 2bc times the cosine of a. And order of operations is going to be important here. Likewise, we could change it up and say b squared equals a squared plus c squared minus 2ac times the cosine of b. Or c squared equals a squared plus b squared minus 2ab times the cosine of c. Now, does everyone agree that this one in particular reminds you of something? What does it remind you of? Pythagorean theorem, exactly. So that's where it comes from, okay? And I want to derive it for you. I'm not going to ever ask you to derive it. You can completely ignore me, tune me out, and focus again in a little bit, but I want to show you where it comes from, okay? And why your teacher didn't show you where it came from last year. You weren't ready for it, okay? You're ready for it now, though. All right, so here's where it comes from. So in right triangle ADC, I dropped a perpendicular here. My height is the perpendicular. And this right triangle, I have a angle A. And the cosine of angle A is going to be the adjacent over the hypotenuse, or x over b. So far, so good? Okay. If I want to solve that get that x by itself, I'm just going to multiply both sides by b. And so x is equal to b times the cosine of a. All right. Also, in this big side, c equals x plus y. So y is going to be the same thing as c minus x. So far, so good? And y could also be called then b cosine a, c minus b cosine a. Okay, this whole thing minus what we just said x was. Okay, now in this other triangle, same triangle, the sine of angle A is going to be the height, the opposite over the hypotenuse, the h over b. And if we get h all by itself, then we're multiplying both sides by b, and so the height is now b times the sine of a. So far, so good? Now, let's go to the other triangle, right triangle CBD. In this triangle, the red triangle, we know that a squared, which is the hypotenuse, a squared equals h squared plus y squared. Okay? Leg squared plus leg squared is the hypotenuse squared. And we said that, oh, wait a minute, h is going to be b sine a. So in place of h, we're plugging in a b sine of a, h squared plus, in place of y, we're plugging in a c minus b cosine of a. So leg squared plus leg squared is hypotenuse squared. We sub them in. If I square b, I get b squared. If I square the sine of a, I get the sine of squared of a. But when I square this guy, it's taking it by its times itself. And when I square it out, I get c squared minus 2 of these bc cosine a's plus last term squared b squared minus cosine squared of a. Let's do some rearranging. Let's keep this guy where it's at, go grab this guy and put him right next to it. and then keep my c squared minus 2bc cosine A to the right side. What do these two terms have in common? Factor it out, we get sine squared A plus cosine squared A plus that c squared minus 2bc cosine A. And what is sine squared of A plus cosine squared of A? 1. Your Pythagorean identity, right? And so A squared is B squared times 1 plus C squared minus 2BC cosine of A. So that's where it came from. It's not some magic. You're never going to be asked to derive it, at least in this level of courseware, right? But I wanted you to see where it came from. All right, so far so good? Okay, so we use it when we have 3 sides or 2 sides and the included angle that's between them. All right, so let's work our way through it. So first of all, I got a little crazy one day, a few years back, and I decided to do a little magic with PowerPoint, see if I could do this. They look the same, left and right sides, right? Okay, watch what happens if we rearrange the equation. We switch the negative BC cosine A by adding it to both sides, and then bring the A squared to the other side. And this is an alternate version to the law of cosines. Okay? This one's often used if you have an angle and you're trying to find the side, right? This one's used if you have the sides and you're trying to find the angle. If it's helpful to you to learn a couple more formulas or what have you, a couple more laws, feel free. Otherwise, we can just use the original as it's written. But cosine of A is b squared plus c squared minus a squared over 2bc. Cosine of B is a squared plus c squared minus b squared over 2ac. Cosine of C would be a squared plus b squared minus c squared over 2ab. I don't care which way you do it, but realize that you're going to have to know them by the day of the test. I won't provide them for you. Make sense? Law of sines is pretty easy. We've got that one memorized already. Law of cosines, we'll just write it down every time and then write the problem in, and it's going to help us remember it. All right, so let's apply the law of cosines and see how it goes. So we have a situation where they've given us angle A is 75 degrees, side B is 12, and side C is 10. All right, can everyone see why the law of sines does not apply here? We don't have a full proportion, do we? We would have the sine of 75 over we don't know equals the sine of we don't know over 12 equals the sine of we don't know over 10. So we can't use the law of sines yet. Everybody cool with that? All right, so this is a good candidate for law of cosines. So I have an angle A. That means my law of cosines is going to say a squared equals what? B squared plus c squared minus 2bc cosine A. Okay, and there's only one solution for this. We don't have to worry about an ambiguous case. All right, so we're going to start plugging some things in. We don't know what A is, so A squared equals, but B squared is 144, C squared is 100, minus 2 times 1, B times C. Well, B times C is 120. 2 times 120 is 240 times the cosine of angle A. All right, combining like terms, we can add 144 and 100, can't we? So A squared is 244 minus 240 cosine of A. Where do you think students tend to make a mistake if they're going to make a mistake on this? Yes, they try to combine the 244 and the 240. But this is like 244 minus 240x. They're not like terms, are they? So we can't combine those. So, but I forgot, we have an A. Angle A all the way along here was supposed to be how many degrees? 75. And so our calculators, our lovely scientific, not scientific, but graphing calculators are smart enough to know order of operations. If we put 244 minus 240 cosine 75, and we're in degree mode, it's going to tell us that a squared is 181.88. So it understands order of operations. And now when we take a square root of our answer, we get 13.5 meters, centimeters, units. I guess it's units here. We didn't give a unit. And then we kind of look at it and see if this was 10, proportionally, does this look like this could be 13.5? Yeah, looks like a reasonable answer. All right, so the hard work is done. We probably don't want to use law of cosines again. Okay, does that make sense? Let's just go ahead and use our law of sines now. Now we have a complete proportion. Sine of 75 over the 13.5 equals, which one do you want to find next? Angle B or angle C? B? All right, sine of angle B over 12. So sine of angle B is being divided by 12, opposite of dividing, it's multiplying. We multiply both sides by the same thing. We're following the rules of algebra, so we'll take the sine of angle B and set it equal to 12 times the sine of 75. Close our parentheses, divided by 13.5 that we found a moment ago. And we get 0.8586. But in order to get to B, the sine is in the way. We have to do an inverse sine of the sine. Inverse sine of both sides is going to give us our angle back. Second sine, second answer, we get 59.2. And then from there, we can subtract from 180. So 180 minus the 75 minus the 59.2 gets us an error if you don't type in what you're saying, 45.8. And that looks like it's reasonably a 45.8 degree angle. All right, so far so good? That's if we know the angle, the two sides in the included angle, we had to find a third side first. What questions do you have about law of cosines? All right, here comes the next piece. So then we're going to go through and work it through again, but this time we're going to have three sides and we don't know any of the angles. All right, so last year it's very, very common for a teacher to say, hey, if you have three angles of a triangle, always, always, always be sure to find the largest angle first. Okay, when your three sides are given. Did your teachers remind you of that last year? Tell you which one to find first? Would they say why? All right. Well, it turns out that if your triangle is obtuse, right? If your triangle is obtuse, then you will get the wrong answer if you use the law of cosines to find the first angle, and it's not the biggest one, and then you use the law of sines after that. Shall we see why? All right, let's find the A or B first. It doesn't matter. Which one would you like to find first? A? All right, let's find angle A first. Let's use the law of cosines to find angle A. So if we're finding angle A, we're going to say A squared equals B squared plus C squared, right? Looks like the Pythagorean theorem, minus 2BC cosine of A, right? All right, so let's plug things in. A squared is 8 squared. b squared is 11 squared, and c squared is 18 squared, minus 2 times 11 times 18 times the cosine of angle A. And we don't know what angle A is. 2 times 11, 22 times 18 gets us 396. All right, so 64 equals, if I add 121 and 324, I get 445 minus 396 cosine of A. What's the next thing I have to do in my order of operations here? We squared things. We combine like terms. What do I have to do if I want to get the A by itself? Subtract the 445. 64 minus 445 gets us a negative 381. All right, so we're going to divide by a negative 396 and do an inverse cosine. So second cosine of 381 divided by 396, they were both negative, so we'll get a positive. And I get my angle A is 15.8 degrees. All right, that seems reasonable. No issues so far. Everybody good with that? Okay. What happens then, though, is when I use my law of sines now, using my smallest angle, not the largest one that we found first, I say the sine of 15.8 over 8 equals the sine of, let's find C now, over 18. Sine of C is being divided by 18. Opposite of division is multiplication. And so we're going to take the inverse sine of 18 sine of 15.8 divided by 8. And it tells me that C is a 37.77 or 37, I guess we're doing it to one decimal point, bless you, 37.8 degree angle. Is there any way that looks like that could be a 37.8 degree angle? No. So where did the problem come from? Remember when we're talking about things in a standard position, everybody's positive in the first quadrant, sine's positive in the second quadrant, right? Sine and cosecant. So when we're at a 37.8 degree angle, it could be this little 37.8 degree angle, but in order to be a function, when we say inverse sine, it doesn't tell us about the 37.8 degree angle here. That could also satisfy this problem, right? So this is 37.8 degrees short of how many degrees? 180. So if you have the foresight to know that this guy is an obtuse triangle, then you would know, oh, wait a minute, it should be 142.2 degrees. We can find out that it's obtuse by saying 8 squared plus 11 squared. How does that compare to 18 squared? And because it's less than 18 squared, it's obtuse. So we could recover from it if we sketched it out and realized this guy should be obtuse, and we need to take 180 minus that angle. So angle C is actually 142.2, and then we can add that to the 15.8 and get 158 minus 180, a 22 degree angle at angle B. Does that make sense to everyone? Or just do that. Find your largest angle first. Now, how do you know which one's going to be the largest angle? Yeah, the largest side is going to have the largest angle, right? So the bigger I open up the side, the bigger the angle becomes, right? That's a triangle inequality theorem. That says if I have a small little angle, it'll have a small opening. A big angle has a big opening. So use the biggest side in your law of cosines. Does that make sense to everyone? Okay. Questions on this one? All right, here comes the last example. And this is Heron's formula. I'm not going to take the time to derive it. You're going to have to trust me on this one. But what happened was, Heron, I'm not sure how long ago, I think he was a Greek mathematician, figured out that if you wanted the area of any triangle, any oblique triangle, and you knew the three sides, what you did was you found the distance around it, the perimeter, and you divided that by 2. Half of the base times the height is the area, right? So I think that's where the dividing part by 2 part comes from. So we say S is equal to the perimeter divided by 2. And then to find the area of this triangle, you take the square root of S times S minus A times S minus B times S minus C. And that's when you have 3 sides. So we had some formulas that we used with the law of sines that we derived, the same time that we derived the law of sines. And it said that the area was 1/2 AB sine C, right? That was easy to use, wasn't it? Or 1/2 BC sine A, or 1/2 AC sine B. Those are very easy to use. But when we have 3 sides and no angles, then we can use Heron's formula. Or use the law of cosines to find one of the angles. And then from there you can do your thing. All right, so far so good? So let's work it out. So we want to find the distance around this triangle, the perimeter of it. We're going to add 11 plus 16 plus 24. And then we're going to divide that by 2. So 16 and 24 gives me 40, plus 11 is 51. We're going to take 51 and divide it by 2 and get 26.5. That's our S. So now, when we want the area, we're going to take the square root of 26.5 times 26.5 minus 11 times 26.5. Thank you. Helps me if I do my mental math correctly. 25.5. I was trying to make that a 53. Good catch. So 25.5 times 25.5 minus 11 times 25.5 minus 16 times 25.5 minus 24. And once again, this beautiful graphing calculator that we have will do the heavy lifting for us, right? But we could also find the individual pieces. So 25.5 times 25.5 takes longer to say it than it does to type it, minus 11 times 25.5 minus 16 times 25.5 minus 24. And we take a square root of it, and we get 72.6 feet squared. All right, feeling good? 4 ways to find areas now. All the sine part plus the 4 formulas, right? But if this is given if you have all 3 sides. All right, so your assignment is going to be in your book, page 415, 5 through 17 by 3s, 23, 24, 37 to 39, 47, and 52, straight from your green sheet. Okay? And I'll be around if you want a copy of that.
All right, let me hit escape. Not showing.